So in this section, we're going to get an in-depth look at friction, specifically the different types of friction and the conditions under which friction acts. So first type of friction we look at is what's known as static friction. So ideally, as we've seen throughout this unit, if we apply a force to an object, that object should start to accelerate as a result of Newton's laws. However, that does not always happen. For example, in reality, if we push on a box or any surface, we'll notice that even if we apply a certain amount of force to that object, the object may not move. We have to, specifically we notice we have to apply a specific amount of force to an object in order for it to accelerate. It's not that Newton's laws are wrong, it's that in these cases we have what's known as static friction acting between the surface of our object and the surface of the ground on which the object lies. So static friction acts to oppose the attempted motion of our object. So if our object is at rest, static friction is going to attempt to oppose the object's change in motion from rest. So that's our beginning idea for force of static friction. We denote with little f subscript s. The force of friction acts when an object is at rest. It will attempt to keep the object at rest and thus oppose any forces applied to the object. So opposes forces that attempt to accelerate the object and acts opposite the direction of motion of the attempted motion of the object. In addition, you may notice that you have to apply a specific level or amount of force for your object to accelerate. It can't just be any arbitrary amount of force. The reason being is that the force of static friction for between two surfaces will always grow in magnitude to oppose forces acting on an object at rest until static friction is no longer able to counter the forces. So static friction can actually grow in strength to counteract the force that you apply. So your object will not move unless you apply a force that is large enough to accelerate the object and large enough to overcome the force of static friction. So as a result, we say that the force of static friction is less than or equal to the maximum strength of the force of static friction. Less than when we start out by gently pushing on the box, and then it grows in strength up until when it reaches its maximum strength. And then once we exceed once we apply a force that exceeds the maximum strength of static friction, the object will begin to accelerate because our force is larger than however high static friction can go for a specific object and specific surface. So now we're going to look at the factors that affect this maximum amount in order to get what the equation is for the maximum static friction acting. So there are two factors that affect the maximum static friction acting on an object. The first is the roughness of two surfaces. Obviously we know that if two surfaces are very rough, then there's going to be more friction acting between them than two surfaces that are very smooth. So we have what is known as the roughness of two surfaces. We quantify this with a material property of the two surfaces known as the coefficient of friction, mu. It numerically quantifies the roughness between the two surfaces and thus is a material property of the two surfaces. The second factor is the contact between the two forces. So in order for friction to act, there must be contact. We quantify this through normal force from one surface on the other and through a surface area and contact between the surfaces. So the more normal force, recall normal force is a contact force between two objects, the surfaces of two objects. So the stronger the normal force, the stronger the force of friction that will be acting as the normal force quantifies the contact between the two surfaces. So we combine these two factors, the coefficient of friction and the normal force, to get our equation for maximum static friction. The maximum of static friction is equal to the coefficient of static friction times the normal force. And hence we have a new equation for static friction. The force of static friction is less than or equal to the coefficient of static friction times the normal force. So overcoming static friction. We'll look at conditions now to overcome static friction. So let's say I'm pushing to the right here with a force F, and then there's a force of static friction acting towards the left. Again, we have the normal force and the gravitational force, but for right now we're just going to focus in the horizontal direction. So an object at rest will only move if the applied force F exceeds the maximum static friction. So we can write that the object will only move from rest if F is greater than the coefficient of static friction times normal force. Again, that being our maximum static friction. Now, if we realize in this case that these two forces in the horizontal direction, the maximum static friction, the applied force F, make up all of our forces in the x direction, we can subtract the coefficient of friction S of static friction times normal force from both sides in order to get F minus the coefficient of friction, static friction times normal force is greater than 0. However, since these are all our forces acting in the x direction, this is actually our net force. So the condition for an object experiencing static friction to move is that our net force must be greater than 0. So in a certain scenario, if we're asked for the acceleration of an object that's starting from rest, we first want to check to make sure that our net force is greater than 0 with the force of static friction. If it's not greater than 0, then our object is going to be at rest, and hence there's going to be no acceleration occurring. So next we move on to kinetic/sliding friction. So kinetic/sliding friction, labeled with lowercase f subscript k, is a friction that acts when an object is in motion. So the equation for kinetic friction is that the kinetic friction is equal to the coefficient of kinetic friction times the normal force. There are different types of coefficients of frictions depending on the type of friction. So for kinetic friction, there is the coefficient of kinetic friction instead of the coefficient of static friction. In addition, note that there's only an equal sign here. There is no less than or equal sign here. So kinetic friction is in general weaker than static friction. So in general, our coefficient kinetic friction is less than our coefficient static friction. The idea being is that once you get an object to move, it's easier to keep it moving than it is to get an object initially moving when friction is acting. So for example, once you start moving the table, it's a lot easier. If we go back to the example of the person pushing the box on slide 1, once that person gets the box moving, it's a lot easier to keep it moving than it is to get it to move. So as a result, that indicates to us that the kinetic friction that's acting when the object moves is less than or weaker than the static friction that acts when we're first trying to get the box to move. Lastly, we look at rolling friction. We'll look at this more in depth in Unit 7, but right now we're just going to get a brief introduction to it. So it's a friction that acts on an object rotating on a surface like we see right here. An object is rotating in the counterclockwise direction and thus moving to the right. Okay? So it acts at only one point, the point of contact between the object and the ground. So as a result, there is not a huge amount of contact between the wheel or object that's rotating in the ground. Hence, rolling friction is the weakest of the three forms of friction due to this extremely small amount of contact right here. So we can actually see this if we think about if we take our box from example 1 and we put it on wheels, it's a lot easier to get that object moving now than it would be if it was just sitting on the ground where we have static friction acting. So summary ranking of the three strengths is that the force of friction due to rolling is less than the force of kinetic friction / sliding friction, which is less than the force due to static friction. So these are a summary of our rankings right here. Again, when an object's on wheels, it's really easy to get it moving and overcome the force of friction. When an object's moving, it's easier to keep it moving than it is to get it moving. And then the force of static friction is the greatest in strength since if an object's sitting at rest without wheels on a rough surface, it's very difficult to get that object to move. So let's look at an example here. A 20 kilogram mass is sitting at rest on a table. If the coefficient of static friction between the table and the mass is 0.35, what external force F must be applied in order for the box to accelerate? So again, with these problems here, we're interested in typically what force must be applied for an object to accelerate, or finding out if an object will accelerate, and if so, what is the acceleration? So in these cases right here, we always have to start by checking that our net force is greater than 0. In this case, we want the block to accelerate, so we have to apply this condition that the net force must be greater than 0 to solve for our force F. Okay? So if we draw our free body diagram, we see that in this case we want the box to move, so the applied force must overcome the maximum static friction. If you're asked for acceleration or you're asked for the force to get an object moving, you always have to start by checking the maximum force of static friction. Because if the applied force on your object is less than the force due to static friction, your object will not accelerate. Hence why we have this condition right here. So, in this case of our free body diagram, we have a force F acting to the right, we have the maximum force of static friction acting to the left, and we have the normal force and force due to gravity, again acting as usual in the vertical direction here. Again, notice that the force due to static friction is smaller than the other arrows, slightly smaller in this case, due to the fact that the force due to static friction, the force due to friction in general, is weaker than the other types of forces. Okay? So we apply Newton's second law, we set the net force in the x direction to greater than 0, so we have F minus Fs max is greater than 0. Or the force applied must be greater than Fs max. Now we can plug in the equation for the maximum static friction, the coefficient of static friction, times the normal force in order to get our general condition right here. So please note that in order to find our normal force now, that means we have to move to the y direction. So in general, for these friction problems, if you're looking for you're going to have to find your normal force, which means you're going to have to move in the opposite direction in order to find your normal force, as we'll see and get more exposure to in class. So to finish this problem, we move to the y direction, where again our object is in equilibrium. So we have sigma Fy equals 0. We're in equilibrium in the y direction. So we have Fn minus Fg equals 0, or the normal force equals the force due to gravity, and hence Fn equals mg. So now that we have the normal force equals mg, we can move back to the x direction, and we're going to have F is greater than the coefficient of static friction times mg. Plugging in all our known values, the coefficient of static friction is 0.35, the mass is 20 kilograms, and the acceleration of gravity, well, as usual, is 10 meters per second squared. We get that in order to get our object to begin moving and accelerating, that we must apply a force that is greater than 70 newtons. So this is the basic setup for friction scenarios, as we'll see in class.